All right, so today we are going to be adding on some more identities to use for finding values of expressions and also for establishing identities. So these are called the sum and difference formulas for obvious reasons. Each of them is either a sum of two different angles that are then have either cosine, sine, or tangent in front of them. So you have the cosine of a sum, the cosine of a difference, and then the same for sine and tangent. And so we're going to be using these in a bunch of different ways. I'm going to try to show you a good variety of examples. Hopefully you'll feel good about the situations you run into after going through those. Again, you do not have to memorize these. These are on the formula sheet that you will receive. All right, so example 1, find the exact value of each expression. So notice that each of these values, each of these angles that we're trying to find a trig value for is not one of our unit circle values. So 75 degrees isn't a unit circle spot, neither is pi over 12, neither is over here 5 pi over 12. So that's why we need these additional identities so that we can get exact values. You do not need a calculator. In fact, your calculator is useless really in this case because it asks for an exact answer. That means decimals are not going to be accepted. On these, there are often multiple correct angle combinations to use. So again, as always, if you did something differently, but you showed all your steps and you got the same answer, then it's fine. So when I look at 75 degrees, what we are trying to do is to write that angle in terms of unit circle angles, either with a sum or with a difference. So when I looked at 75, the first thing I thought of, 75 is 45 degrees plus 30 degrees. So I'm just rewriting 75 as a sum. I haven't changed the value at all. When I do that, that means I can now use this formula, the cosine of the sum formula. And so in this case, we have alpha and beta are the two angles, so alpha, beta, and then I just substitute those values into this identity. So it says cosine alpha, so in this case, cosine 45 degrees, cosine beta, so cosine 30 degrees, minus sine alpha, sine beta. Now, everything is in terms of unit circle values. These ones I really should have memorized, but of course, you can always look at your unit circle if you need them. Remember that your cosine values are the x values. So I've got my 45s here, cosine, sine, 30, cosine, sine are here. So now I'm just substituting in those values. So cosine of 45 degrees is radical 2 over 2. Cosine of 30 degrees is radical 3 over 2. Then I've got minus sine 45, which is radical 2 over 2, and sine 30, which is 1/2. And now the rest is just algebraic manipulation. So multiply these first two, that's radical 6 over 4. Minus over here, when I multiply, I get radical 2 over 4. They already have a common denominator, so that means that I can go ahead and write them as one fraction. Sometimes, like when you're checking answers in the back of the book, sometimes you might see them write it like a 1/4 out in front and something like this. This answer is totally acceptable, but just so you realize that those two things are equivalent, they might write it a little bit differently when you're looking at and checking an answer. All right, so B, same idea. I'm going to draw a little separator here. I've got pi over 12, and pi over 12 is not on the unit circle. And because pi over 12 is smaller than the values on the unit circle, then I'm thinking, okay, if it's smaller, then that means I'm going to be using a difference using subtraction here. So a denominator of 12 I could get by using 3s and 4s, right? And so I think of pi over 3 minus pi over 4. Because if I have pi over 3 minus pi over 4, if I rewrote those with common denominator of 12, that's 4 pi over 12 minus 3 pi over 12, which is indeed pi over 12. So I'm just proving to you why pi over 12 is the same as pi over 3 minus pi over 4. So we're going to rewrite this as tangent of pi over 3 minus pi over 4. And again, now everything is in terms of a unit circle value. I can use my unit circle to find my tangents in combination with my tangent difference formula. So my alpha in this case is pi over 3. My beta is pi over 4. So I'm going to do tangent alpha minus tangent beta over 1 plus tangent alpha tangent beta. All right, so now again I'm going to evaluate. So the tangent at pi over 3, and again, some of you may have these memorized. Tangent, remember, is the cosine divided by the sine. Pi over 3 has 1/3, so if you're memorizing, it's the radical 3 is the answer. If you don't have that memorized, then simply do the division, radical 3 over 2, which is the sine, divided by 1/2, and you get that same answer. So tangent at pi over 3 is equal to radical 3 minus the tangent at pi over 4. Well, at pi over 4, the sine and the cosine are the same, so the tangent is 1. So that is up here. And then my denominator, 1 plus, and then they're the same values, so it's radical 3 times 1, which obviously will just be radical 3. So I've got radical 3 minus 1 over 1 plus radical 3. I cannot leave it like that because I've got a radical in the denominator. So just like you did in Algebra 2 when you had these, I have to rationalize by multiplying by the conjugate. So multiply both top and bottom by 1 minus radical 3. So on the top, I have to double distribute that. So this, 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 and this. And so I get radical 3 minus 3 when I distribute the radical 3. Then I have to distribute the negative 1, which gives me negative 1 plus radical 3. In the denominator, the whole point of those conjugates is that the insides and outsides drop out. So all I really need to do are the firsts and the lasts. So 1 times 1 is 1. Radical 3 times radical 3 is 3, and it's a minus on it. And now I'm going to combine like terms. So radical 3, negative 3, negative 1. Those are all like terms. So I'm going to combine those. So that gives me negative 4 plus 2 radical 3 in the top. And in the bottom, that gives me negative 2. And then I can actually divide because both of these terms are evenly divisible by negative 2. So that gives me positive 2 minus radical 3 for my final simplified answer. All right, last one of this type. As you can see, this one, I'm working backward. Instead of starting with something small and using the identity to expand it, I'm looking at something that is in the identity form, and I want to put it back together. So this is like a matching game at first. So I look and I say, okay, which one has cosine, cosine plus sine, sine? So I look, cosine, cosine plus sine, sine is right here, and that's the difference of cosine. So this takes the form of cosine alpha minus beta. In this case, my alpha is the first one, so 5 pi over 12. My beta is pi over 12. So alpha minus beta is, if I make this cosine 5 pi over 12 minus pi over 12, that becomes cosine of 4 pi over 12. 4 pi over 12 obviously reduces, so that becomes the cosine of pi over 3. And so now it's a unit circle value. So find your pi over 3, the cosine, there's the answer, 1/2. All right, so different manipulations that we can use. Again, calculator's pretty much useless here because we need exact values for everything. So radicals and whatnot. All right, example 2, if the cosine of theta is 1/4 and theta is in quadrant 4, find the exact value. So what I need to do here, because obviously this value for cosine is not a unit circle value, so that means that, we are going to want to draw the triangle. So again, theta is in quadrant 4. So the first thing I'm going to do is draw a quadrant 4 triangle. Remember that our angles always have their right angle on the x-axis, regardless of what quadrant they're in, and the theta should be coming off of the origin. So this is what it would look like. If the cosine is 1/4, cosine is adjacent over hypotenuse. So that means that this is 1 and this is 4. And so I can then use that to find the opposite side. So 1 squared plus x squared equals 4 squared. So 1 plus x squared equals 16. X squared equals 15. And so that means that this side is radical 15. Again, we've talked about technically, of course, side lengths can't be negative. I usually label it that way just because we've moved down because it's giving us the coordinate. But you can just do a check at the end. If you prefer, make sure that your answers line up with the signs that you know you should have, because in quadrant 4, if we think all scholars take calculus, cosine and secant are going to be positive. Everything else should be negative. All right, so sine of theta, I look at my triangle. Sine is opposite over hypotenuse. Again, I know it should be negative because we're in quadrant 4, and that's all the work I have to do. Finding that side was all I needed to answer that first question. Now, in B, I obviously am going to have to use one of my new identities because I've got a difference here, and I know that I'm going to have to use my theta, and I'm going to have to use the formula for sine difference, which is right here. So sine alpha cosine beta minus cosine alpha sine beta is what I'm going to use. Again, of course, the theta becomes my alpha. The pi over 6 becomes my beta. So this is going to be sine theta cosine pi over 6 minus cosine theta sine pi over 6. Now, for the theta, I'm going back to this triangle every time. So sine of theta, I already just wrote. but that value is negative radical 15 over 4. Cosine of pi over 6, that's a unit circle value. So here's pi over 6, here's my cosine value. So radical theta 2 goes in there. Minus cosine theta, that was in our given, or you can look at the triangle. So 1/4. And then sine of pi over 6 is the y coordinate there, so that's going to be 1/2. And now some algebra. So when I multiply these, I get negative radical 45 on the top, 8 on the bottom. Down here, I get minus 1 over 8. Now, radical 45 needs broken down. So over here, remember that radical 45 is the same as radical 9 times radical 5. So 3 radical 5 is what that guy is. So I've got negative 3 radical 5 minus 1 over 8 for my answer. All right, for C, cosine theta plus pi over 3. So same idea. I got my alpha, I've got my beta, and I need to use one of the identities, in this case the cosine sum. So cosine sum is cosine cosine minus sine sine. So cosine theta cosine pi over 3 minus sine theta sine pi over 3. And just doing the exact same thing. So cosine of theta, again, was one of our givens. So that's 1/4. Cosine at pi over 3 on my unit circle is 1/2. Minus sine of theta, negative radical 15 over 4. And sine at pi over 3 is radical 3 over 2. So in this case, I get 1/8 minus, oh, no, it's minus a minus, so plus radical 45 over 8. So I get almost the same thing that I got in my last problem, but I have addition between them, so this is obviously going to simplify the same way it did over here. So I've got 1 plus 3 radical 5 over 8. And again, like I talked about up here, it's possible that when they list the answers, they might put a 1/8 out in front. It's equivalent. Both of those answers are fine. Just make sure that you've rationalized things and you'll be good to go. All right, last one here. We are using tangent difference. So alpha and beta. So tangent difference is this one. So tangent of theta minus tangent of pi over 4 over 1 plus tangent theta tangent pi over 4. So we haven't done tangent yet, so I need to look back over at my triangle. Remember, tangent is opposite over adjacent. So that'd be negative radical 15 over 1. So just negative radical 15 is the tangent of theta. So we'll plug that in. And then minus tangent at pi over 4. We've already done in an earlier problem. That is 1. And then 1 plus negative radical 15 times 1. So negative radical 15 minus 1 over 1 minus radical 15. And then you're noticing some patterns, hopefully, by this point. So same thing I have to do here as what I did up here when I had the tangent. I need to rationalize, so 1 plus radical 15 is what I need to multiply the top and bottom by to do that. So on the top, I've got negative radical 15 times 1, and then negative radical 15 times positive radical 15, which is a minus 15. Then distribute the 1, or negative 1 rather, so that gives me minus 1, and then minus radical 15. On the bottom, again, because it's a sum and difference pattern, I really only need to multiply the 1 times the 1 and the radical 15 times the negative radical 15. So 1 minus 15 is what I will get there. So on the top, like terms, negative 15 minus 1 is negative 16, and these two both negative, so minus 2 radical 15. And then on the bottom, that gives me negative 14. So unlike up here where we could just divide by negative 2, these are obviously not evenly divisible by negative 14, but they are all evenly divisible by negative 2. So all the negatives turn into positives, and I need to reduce them. So 16 over 14 is 8 here, 7 there, and then obviously 2 becomes a 1, and all the negatives turn into a positive. So 8 plus radical 15 over 7 is going to be my final answer there. All right. Hopefully these are making sense. I've tried to choose a lot of different examples to hopefully give you some strategies for manipulating the algebra. In example 3 now, we're establishing the identity. So go back to, your 8-4, look at strategies that we talked about for dealing with trig identities. So all of the different things that we might need to do to get these to work. So when I look at A, the left side certainly looks more complicated than the right side, so I'm going to start with the left side. And that one, of course, screams difference identity. So looking at my formulas, I am going to use my cosine difference one. So cosine, cosine plus sine, sine. In this case, alpha and beta. So using that pattern, I've got cosine pi, cosine theta, plus sine pi, sine theta. Cosine of pi is a unit circle value, so that is -1. Sine of pi is 0. So substitute those values in. So I've got -1 times cosine theta here. Over here, I've got 0 times sine of theta. So 0 times anything is 0, which means these are going to cancel out. That becomes a 0. -1 times cosine theta is the opposite of cosine theta, which conveniently gives us our right side. So we have established the identity. All right. So when I look at B, the right side looks more complicated, but it also has cotangents. And I'm going to show you a strategy that they do sometimes in the homework. So I want you to understand this strategy. So this, if I try to multiply, it's going to make it a lot more complicated. So what I am going to do is I'm going to rewrite cotangent as cosine over sine, and then use my two identities. So I am going to start with the left this time, again. And so again, cotangent is cosine over sine. So cosine of the angle over sine of the angle. And now each of the numerator and denominator are one of our new identities. So cosine sum identity says cosine alpha cosine beta minus sine alpha sine beta. And on the bottom, I have the sine sum, which is sine alpha cosine beta plus cosine alpha sine beta. All right, so when I look at this, this is a new strategy that until you see it, you would never think to do it on your own. But once you've seen it, then you can see how to use it and where it might be helpful. Here is why, because again, we talked about how these identities are kind of like playing chess and you have to like think ahead to try to get it to do the right thing. I want this to go back to cotangents eventually. Notice that by using these two identities, I do have the signs right here. I've got something minus something else on the top, and I've got a sum on the bottom. So that's good news. But what I have in front here are cosines, and I want cotangents, but of the same angle combination, right? It's alpha and beta. And I want it to stay alpha and beta, but instead of cosine, I want it to be cotangent. So in order to get from cosine to cotangent, I would need to divide by sine. Now, it has to be sine of the same thing, right? If I want cotangent alpha, cotangent beta, I need the sine of both of those. So I'm going to divide both sides by sine alpha sine beta, because that makes these two cosines divided by sines. So when I do that, whatever I do to one part of an equation or an expression, I have to do to the whole thing. It's just like rationalizing. Whatever I did to the bottom, I have to do to the top. So all of the terms have to get divided by the same thing, or you can't use that strategy. So if I grab a different color here for just a minute, this is my original division sign. I'm taking now my numerator, and that first term gets divided by sine alpha sine beta, because again, that's going to get me cotangent alpha cotangent beta. So whatever I do there, I have to do to the other part of the numerator. So divide by sine alpha sine beta. Whatever I did to the top, I also have to do to the bottom. So sine alpha cosine beta divided by the same thing. So sine alpha sine beta, and then plus cosine alpha sine beta divided by the same thing as everything else. Again, would you probably have thought to do this if I hadn't shown you? Probably not. But now that you've seen it once, it's in your tool bag of things that can be helpful to get a manipulation that is going to help us verify. So now what do I have? Well, the whole purpose, the reason why we thought to do this is so that we could get this first term correct. So that has now turned into cotangent alpha, cotangent beta. Notice that this is 1 because it's the same thing on the top as it is on the bottom. So minus 1, that part's good. In the denominator, notice that I've got things that cancel. Those cancel, and those cancel. So now I've got cosine beta over sine beta, which is cotangent beta, and cosine alpha over sine alpha, which is cotangent alpha. So that now is exactly what is on my right side. So, new strategy to divide all the terms by the same expression in order to manipulate it into what you need. All right, hopefully that gives you enough examples that you feel confident on your practice, and of course we will have time to answer some questions next time I see you.